Oh, okay, can you hear me? Okay, thanks again to the organizers for inviting me, and I will discuss here the some strong coupling in physics in some sense. So it's a Mott transition in multi-orbital Hubbard models, and it's first orderness in some situations. And what is the effect for the doped phase diagram in these models? But then there is a clear link with Hund's metals and iron-based superconductors in some material studies towards the end of the talk. So you will see also that there is a link with an analogy with the physics of the cuprates, even though these, of course, are single band materials. So this is mostly the work of Maria Hassiel-Efteriou and some of the work of Pablo Villar-Ribi, who were PhD students in my group. And work has been done in collaboration with the Würzburg group and the Trieste group in CISA, and all the rest in ESPCI in Paris. So multi-orbital Hubbard models, I will be very short on this. In the beginning of the talk, I will just address models, but then this single body part can be indeed a fully realistic tight binding coming from DFT, but the important part is that we have several orbitals on each side, and the electrons in these orbitals can interact with an interorbital interaction, which we parameterize with U, but also reduced interorbital interaction and a preference for aligning their spins, and these are parameterized by what we call the Hund's coupling, which is the parameter J that embodies the Hund's rules known in chemistry. Now we solve these models with dynamical mean field theory or slate spinning field, which are simplified versions of thereof. So the thing on which I want to drag your attention is the fact that the Mott transition at half filling in these multi-orbital models is first order as soon as Hund's coupling is present. So only for J equals 0 you will have, this is the quasi-particle weight that measures the inerrancy, the metallicity of the system, and when it vanishes it signals Mott transition. And only when J is 0 you will have continuous vanishing. Otherwise, and it's well established through a lot of different techniques, at least at the model level, you will have a first order jump from a metal to an insulator. Now we have studied this to the state-of-the-art accuracy with a zero temperature, with a numerical renormalization group as an impurity solver for DMFT, and indeed we can reproduce this jump. So this is the same quasi-particle weight Z, and as a function of the interaction strength for some finite Hund's coupling, we have the metallic branch that ends and doesn't touch the insulating branch, which is this red Z equals 0 branch. On the other hand, we could realize, which is maybe expected, but it's nice to be able to calculate it exactly, that these two branches are actually connected through an unstable metallic branch that then gives this sigmoidal shape to the Z versus U curve, which is really a hallmark of first orderedness. And in fact, you will have a jump whenever the two, this sigmoidal bounds the energies of these two solutions cross at some point in the coexistence zone, and the actual transition happens somewhere in the middle here where the two energies of the stable branches cross. Now, what happens when we go to the doped phase? Well, if we start from a value of the interaction strength in this coexistence range, where you have a half filling both metal and insulator, the metallic solution will be doped immediately as soon as you move the chemical potential away from the particle of symmetric chemical potential that we were using for the half-filled case, whereas the insulator will remain undoped, and only after the chemical potential has reached the Mott gap will be eventually doped. Now, obviously, when you go to a larger U, where the half filling, you don't have these two solutions, you will have like this blue curve metallic solution, which will not reach obviously half filling. But the important part is that these two branches are still connected diabatically through an unstable branch, and this will continue on and on when you increase the interaction strength U, so that for a while you will have a sigmoidal shape sigmoidal shape joining the metallic branch and this doped Mott insulator branch, which is still a metal, but is connected to the Mott insulator and has a much reduced quasi-particle weight compared to the close by metallic, purely metallic solution. And then at some point, this sigmoidal shape will straighten out, and one will remain with just a monotonous branch with just some inflection point. Now, all this can be put on a phase diagram, and what is very nice is that the phase diagram looks like this. So here at half filling, you have a metal, and this black bar signals the Mott insulator. So this is exactly this image here, with this coexistence range in the middle, the dashed part. Now, when you dope, what you have is that, if you look at here, you have a zone in doping where the two stable branches actually overlap. So you have two solutions here. But very quickly, you are left instead with the part where only the unstable solution exists at some doping. And this gives this no solution region. And all these, of course, merge into a point in which you have a continuous curve, and it's this quantum critical point. And after this, you just left with a crossover. Now, the important part is that then this sigmoidal shape calls for another Maxwell contraction, which actually originates this shaded phase diagram over here, which then really is the final shape of the phase diagram at the end of the doped phase, where you have this metallic phase, which is connected to the half-filled metal, which then undergoes a first-order transition not to the Mott insulator, but to another metallic phase, which is instead adiabatically connected to the Mott insulator half-filling. And these are intercalated between these two phases. There is a zone of phase separation that ends in a quantum critical point. And then you have a crossover. Now, it's very nice to understand this in a plastic way through a 3D plot in which you can actually just imagine that there is a folding of the equation of state. So the equation of state, of course, is continuous, and it's folded in the parameter space, interaction strength, chemical potential. And the folding makes that you have, of course, you cut this folding somewhere in order to construct to do the maximum construction. And if you see, if whatever you plot in this interaction chemical potential plane, here we're plotting the quasi-particle weight. So this upper curve here gives rise to this cut, golden cut over here. If you cut on the other way, you have this curve done at fixed interaction strength for various varying the chemical potential, and these are these curves. Obviously, you have to plot the doping as a function of the same two parameters, but this blue curve corresponds to this other blue curve. So basically, these curves, doping as a function of chemical potential and quasi-particle weight as a function of interaction strength, are just the cuts of these plots of the equation of state, which, of course, here we're plotting different things, but the folding is the same for all because it's a characteristic of the solution of the problem. So indeed, what this shows you that the first order character half filling implies the first order character of the transition when coming from the doped side, and so there is an obvious implication of the existence of this quantum critical point at some point, because of course you have this folded equation of state at half filling, but if you go at very large doping, you expect all signatures of Mott physics to be wiped away. So this folding has to unfold at some point, and this necessarily implies a quantum critical point, which we numerically, generically sound as finite doping. So the key message here is this: if you have a first order Mott transition, then you will have a quantum critical point, which generically is seen as finite doping. Second point is that the Hund's coupling makes this transition first order, and so this quantum critical point as finite doping is implied by a finite Hund's coupling in any multi-orbital model. Now, why the one key point I would like to underline is why the Hund's coupling makes the transition first order. And it's not obvious, to do this in a very short talk, but we did a Landau analysis through the Slade spin mean field, which is a simplified version of the MFT, and in which the Mott transition is pictured I mean, the system is described with quasi-particles, of which the renormalizations are calculated through an auxiliary system of spins on a lattice. And the Mott transition is mapped into a ferromagnetic to paramagnetic transition as a function of the interaction strength. And so the Mott order parameter, which in this effective system of spins on a lattice is the spontaneous slave spin magnetization, embodies the effect of the quasi-particle weight. So when it goes to zero, you go to the paramagnetic phase, and the quasi-particle weight goes to zero. So you can do analysis, a numerical analysis of these slave spin and field equations, and of course, this reproduces very well the sigmoidal shape of the Z versus U curve. If you apply a driving field, you can do you can explore the landscape of the competing solutions out of equilibrium, and indeed you can see here is an example in which I see this red curve is a curve that you obtain for the Landau energy for a U smaller than you critical. So you have only one minimum, so a stable solution at finite order parameters, so at finite Z. This is the metallic solution. When you go to large U, you get this golden curve here. So the minimum is at zero. This is the metal. The insulator, the Mott insulator. And then in the middle, you have this characteristic two minimum solution, two minimum shape, which indeed makes the transition first order. So that when these two minima cross in energy, you jump from a metal to an insulator. This is what happens around filling. Now, this is also what you did. The same topology of the curves is brought in the finite-doping plane, and it's what gives the composition of the first order of the two of the transition between the two metals. Now, why the Hund's coupling causes this? This can be done by doing the analysis of the Landau energy, and you know that this double minimum structure is due to the fact that in order to have a first order transition is well known, you have to have a quartic coefficient in the expansion of the Landau free energy, which is negative when the second order coefficient changes sign. Okay, so that you have this maximum, and then higher order coefficients imply a second minimum here. So this can be calculated analytically in slave spins, and I won't enter into the details for shortness of time, but it can be shown that if you calculate the ground state energy of the slave spin system as a function of the effective field, which is so the Weissman field that has been used in order to treat these effective spins on a lattice, you can evaluate, of course, this perturbation expansion as a function of the field in several order in perturbation theory, and the quartic coefficient of the ground state energy has the same sign than this gamma 4, this quartic coefficient of the Landau free energy. Yes. So I will be short in this, and I just say that we can calculate this, and it's always negative at finite Hund coupling, and this is understood in perturbation theory simply because this is the atomic, the sketch of the lowest lying states of the atomic state when you have Hund's coupling. You have a triplet state which is low lying and is split from the singlet state in the half field sector, whereas you have charge excitation to the n+1 and n-1 sectors of charge, and it's seen that second order processes in this perturbation theory can only bring you one charge up or down. So it's going it's equivalent to going back and forth on this A process, where fourth order processes can bring you to this state which is low lying. So the key point is that these processes, these connected processes that brings you to this low lying state in the same charge state are only reached through 4 jumps. So it only contributes at the fourth order. So this is what makes the fourth order coefficient negative, is the fact that this splitting energy, which is the denominator in perturbation theory, is very small, is J, whereas the charge excitations are split by order U, and which is larger. So this will prevail, this negative process will prevail on this one and makes the fermentation first order. So the takeaway message is that whenever you have an atomic spectrum in which you have a small splitting of the ground state, this will lead you to, this could be due to crystal splitting, or in this case, the Lorentz coupling, or to Young-Teller. This will lead you to a first order Mott transition because this distance is much smaller than the charge expectations. Now, the last minutes, I just want to show you what is the implication for real materials. So, elements of realism have been added in other further studies where we put like 3 orbitals, 5 orbitals, crystal splitting, and all these shows that this zone of phase separation that I showed you in the phase diagram extends more and more. And it can extend from the few percent of doping, it was about 10% in the 2 orbital Hubbard model, even to let's say 1 electron of doping or 1 hole of doping away from the half-filled Mott transition in 5 orbital models with crystal splitting. So it becomes relevant for the next geometric filling, for instance, 6 electrons in 5 orbitals, which is exactly the geometric filling of the iron-based superconductors. So, and for the iron-based superconductors, we have done several studies for the 1, 2, 2 families, for the 1, 1, 1 family, for the chalcogenides, and in all these we could, via DFT plus slave spins, show that there is a zone of phase separation, and indeed a crossover after it, dividing a zone of weakly renormalized metal from a strong coupling metal with in strong orbital selective correlations, crossing the interaction doping plane in all of these materials. And this I can detail a little more, but if I have a little more time, it relates very well with the trends, experimental trends of the TCs. So basically, when the compound is on top of these instability zones, we find high TC experimentally. The last point is that there is a very analogous scenario for cuprates in which a zone of phase separation originates from the Mott transition at half filling and crosses the interaction doping plane and divides the pseudo gap from the weakly correlated Fermi liquid. And all this is somehow an effect due to the half filled Mott insulator that extends its influence in doping. So we have a provocative scenario commonly for iron-based superconductors and cuprates in which basically, I mean, this is the dome of superconductivity that you will get if in the iron-based superconductors if you acknowledge that this antiferromagnetic phase is incidentally produced by the stoichiometric filling, and you have a dome of superconductivity in between a weakly correlated Fermi liquid and a strongly correlated selective metal, and all this originates from the Mott insulation, the insulator that you get at half filling. So these are my conclusions, and sorry for being so short. I had only 20 minutes, and it was a little compressed. Thank you very much.
Yeah, very nice talk. I have questions. So of course, you mentioned there's crystal field and also different bandwidths. So this is the ideal case that you're looking at. So would that be always relevant perturbation if you have a smaller bandwidth difference? Would you still have the quantum critical point?
The quantum critical point is pretty robust, and if you have crystal field splitting, it actually moves further away in doping. Now, we didn't study indeed all the combinations of crystal field and bandwidth differences, but it's pretty robust. The only difference with differences in bandwidth between bands is that the zone of the strongly correlated metal is very prone to orbital selective correlations, so you can get a zone of orbital selective Mott insulator between the metal and the full Mott insulator. That's the main effect.
Yeah, a short question. So, very quickly. So, do you have an hand waving number for the U to enter the orbital selective regime or the Hund regime? Say you can also reach the other metallic regime for smaller U where you don't see Hund metal physics at all. So is there
the only rule of thumb is that you have to estimate where is the Mott insulator half filling, and that's more or less the U from which you will get this whole physics.
So at the beginning you had a SZ symmetric Hamiltonian instead of SU2, but from your talk I understand it doesn't really matter so much. So could you briefly discuss
Yeah,
what
you mean
changes in
what happens if I put like
SU2 symmetry versus Z2 symmetry?
we have done the same calculation with Calamari and we still have the Mott transition very clearly at half filling and the same phenomenology for the doping. So no difference.
But it should be quantitatively much less pronounced, right?
Quantitatively less pronounced. We did the study with slate bosons in okay, I cannot move anymore, but okay, it was here at some point. Yeah. And yes, there is a reduction. Basically, the idea is that when the more the system is symmetric, the more the fluctuation wipe out this mechanism. But so this is the kind of Mori phase diagram, and this is the density phase diagram. It's just what quantitative difference. Yes.
Nice talk, Luca. The question is about maybe you can give us a physical intuition about what your quantum critical point means. So in a quantum critical point, we're thinking typically of a phase transition that's as a function of quantum fluctuations. And you had your quantum critical point appearing as a function of chemical potential. Can you give us an intuitive sense of what is the thing that's experiencing more quantum fluctuations that drives this transition?
Yes, there's two things there. So physically is a density. So that's because we have diverging compressibility and the two spinoidals merge in this quantum critical point. So it's really the density and the electronic density. And associated to that, there is the fact that the two metallic phases have a huge difference in quasi-particle weight. So there is some associated fluctuations of metallic character, if you want, if you're able to define that locally somehow. Okay, so it's between a very good metal and a very bad metal. I haven't fully explored that. Thank you.